Okay, so we can start. First of all, good morning. Still in the morning. So I'm Jose Serra. I'm coming from ITQ CSIC in Spain, in Valencia, and I will chair this parallel session 3A. So I asked the presenters when they are presenting to switch on the camera and of course the micro, and when you finish your slot, you switch off. But also during questions, it will be nice that you keep your camera on. Also, please leave some minutes for questions. That will be nice, and not use the 20 minutes for your presentation. So then I'm happy to introduce the first speaker, that is Dr. Antonio de Paula Oliveira. He's gonna talk about sorption enhancement of reforming and water gas shift for CO2 capture and experimental results. So, Antonio, the floor is yours.
Thank you so much. I hope all of you can hear me well.
Yes.
I will start sharing my presentation now.
So you can write questions in the chat. Okay.
Can you see my slides?
Not in full screen now. Yes.
Yeah. Excellent. Then. So thanks again, Jose, for the introduction, and also wants to thank the organizers for the invitation for us to show our work here. The work that I'm going to be presenting today is part of the work package 3 of the Converge project that has already been presented yesterday by Gianpaolo. And this specific part is related to the sorption enhanced reforming or sorption enhanced water gas shift for CO2 capture and hydrogen production. And the main objectives of the work package as a whole, which is regarding the integration, as you can see here in this picture, is the integration of the sorption enhanced reforming with the electrochemical hydrogen compression. And the start of this project is with waste, feedstock, and biomass being gasified, and then there is the catalytic cracking and cleaning of these gases, and we start to do the reforming to produce hydrogen and CO2 in different streams, which is further cleaned and compressed to produce methanol that will be used for biodiesel production at the end. And our main objectives in this work package is to reduce the energy consumption of the hydrogen productions, and the work that we are doing at IFE is mainly related to the optimization of the CO2 solvent material that's going to be used, as well as the development of a new improved catalyst. Our partners in these projects are taking care of the remaining activities that are the related of the hydrogen purity and further compression to 50 bars. And later, next year, we're going to be running a test campaign in our facility that comprises of 500 hours of test integrated SCR with the electronic hydrogen compression. For those that are not familiar with SCR, Sorption Enhanced Reforming means, this is a process that does the production of hydrogen by reforming syngas or natural gas at the same time that we are capturing the CO2. So this system comprises of mainly two reactors, where in the first one is done the reforming, where the catalyst and sorbent are in a fluidized mode here, and once this sorbent reach its limited sorption capacity, it then goes to a regenerator. And we take in this process advantage of the Le Chatelier process by shifting the equilibrium towards hydrogen with the removal of the CO2 in this process. I will come later to some of the advantage of doing that. And for the purpose of this work, we are using the SCR or SEWGS for convert the feed gas that from biomass gasification after it passed through the catalytic cracking. So this is the composition that we have at the end. You can see that's a syngas with traditional composition of hydrogen and CO, but we also have a large amount of methane and some ethylene that's more complicated to deal with. The way we work in this system here for the later test is with a dual bubbling fluidized bed reactor, where we have the reform here in the first stage, and as I mentioned before, once the catalyst, the sorbent reaches its capacity, we need to tailor this mold, this circulation rate. We have then our materials being passed through this riser and reach the regenerator, where here we're going to be bringing back our sorbent to its natural capacity and then inject back here. So as I mentioned, the work that we were doing first, it was trying to improve the sorbent that we have already developed here in IFI and test long. And the way that we try to improve the capacity and the stability of the sorbent was by adding some dopants. So we tried three different dopants, as we can see here, in a calcium oxide mionite sorbent. Unfortunately, we had good stability. This is capture capacity, and this is number of cycles, okay, in all the three pictures here. So when we were trying these sorbents in its powder format, the sorbent capacity was quite stable towards many cycles. But when we need to do the pellets, not the pellets, the particles in the size that we need for fluidization, this material become a bit unstable. And after 50 cycles, we start to have a decrease that was lower than the target that we need to put for converge, which was 30 grams of CO2 per 100 grams of materials. Because of that, we reached a point that we decided to go for our backup options, that was to use the sorbent that we have already developed in the past and has its stability guaranteed even after 1,000 cycles. As you can see here, even after 1,000 cycles, we have a sorption capacity over 20 grams for 100 grams of sorbent. So now this is the sorbent that we are using here for our experiments. In addition to the sorbent, we also want to develop a catalyst for the converge process. And the reason for that is, today in the market, there is no catalyst that's dedicated for sorption enhanced reforming. And also those catalysts that are there that are traditional for reforming, they don't come in particle size that are required for our process, which means that the commercial catalysts that are out there, they come in pellet format. We need to crush this catalyst, sieve to get the particle size that we need, which means that we have a few problems during this process. First is the additional cost for processing this to crush and sieve. Second is the loss of material, because more than half of it doesn't become the particle size that we need. And third, the particles that we have in the end, since they are crushing, they are not proper spheres and they have sharper edges, which means that they are more prone to attrition and in the fluidized bed in loss of materials. So we decided to develop our own catalyst for that. And also to develop a new catalyst, we need to develop a new catalyst that not only has the physical conditions better than the commercial catalyst, but that also has chemical conditions that are improved. And the main one is the commercial catalyst is very prone to sintering after passing through the regeneration step. It works really well just doing reforming, but when it needs to be regenerated together with the sorbent, this catalyst start to sinter. So for this, we developed a method here for all the catalysts that we have synthesized. That first we test this catalyst in a fixed bed to test its conversion capacity and compare to the commercial catalyst, and then we add this to an aging step where we put this catalyst under the conditions of regeneration for many hours. So here we start working with steps of 60 hours. So we age this catalyst for 60 hours, and then we test it again in our cycle here, and we keep doing that until we see the deactivation or sintering of these catalysts. In this process, we have tested over about 15 to 20 new materials with different supports that we applied, and also different nickel loadings until we reach what became our reference converge catalyst, the catalyst that we're going to be using in our process. And just to give you a broader idea here, this is the sorption SMR conversion. We are not talking yet about doing the process with sorbent. This is just to see the capacity of this catalyst to reform methane. So it's just methane and steam pass through the fixed bed reactor. First fresh, we check the conversion, and then aged, we age for 60 hours, and we check the conversion again. And you can see here now that in the first test already, when we do with the conversion catalyst, there is a drop in the conversion capacity of the reference catalyst, and this is explaining that there is an enormous amount of sintering after 60 hours of aging. While in the converge catalyst that we have selected, we have no evidence of sintering until 60 hours. Of course, we need to test this longer, and we have done longer tests, and those that are going to come now. And the next text, they are pretty much side-by-side comparison of our catalyst, fresh and aged, with the reference commercial catalyst that we have there. So in terms of methane conversion, in this axis is methane conversion, and here we test this, we stress the catalyst for different high gas space velocities. We have here the solid lines are the both fresh catalyst, where the green one is the converge catalyst. So we see that for lower gas space velocities, we outperform the commercial one, while for higher gas space velocity, they are very similar for the fresh. But when we age this catalyst, the disparities start to appear. And this is related mostly to sintering, and also some coking that we observe that you're going to be able to see in the next graph. The same applies for hydrogen concentration at the end. When we measure the hydrogen concentration, we can see that the converge catalyst also has better selectivity than the commercial catalyst. An additional problem that we face with the commercial catalyst is that when we put this catalyst under SMR conditions for a long time, we start to see the deposition of carbon. And these many studies in the literature show that's mainly due to the ethylene that is not being reformed but cracked. So in this graph here, in reference to the commercial catalyst, we are showing just the outlet flow of the reactor. And so I want you to focus on the yellow solid line here that's related to the, we call it missing carbon. So when we do the mass balance at the end, we don't find this carbon exiting the reactor. And we can see that after many tests, we run with the fresh catalyst, so low deposition. And then we age this catalyst for almost 24 hours. We run another SMR test, another aging to the point of 88 hours, and then 112 hours with SMR tests in the interval. We can see that the missing carbon increased a lot during the aging test, which was later confirmed by us doing TPO tests. And as you can see here, this test stopped in 112 hours because the amount of the carbon deposition was so high in the later test that we tried to do, that the pressure drop in the reactor was to an extent that that we could not work with it. So we need to stop the experiments. When we go to the converge catalyst, you can see here that the missing carbon is pretty much stable even when we run after 150 hours. So, and this missing carbon here can be even considered within the error margins of the calibrations of the experiments. So we don't see the same deposition that we do here. And once we have tested this material and optimized the process for heat production, we start testing this in our fluidized bed test rig. And it's in this fluidized bed test rig that we're gonna work on the main parameters of the process, such as temperature, steam to carbon ratio, fluidization velocity, and so on. And there is a lot of trade-offs here that we need to think, because at the end it's not just about the hydrogen quantity at the end, but also for the cracking of the ethylene, which is not welcome in the electronic hydrogen compression, and also CO. So we need to find a balance. So here, for instance, we run some equilibrium calculations for the converge for our process, and we see here that with the increase of temperature between 550 and 700, when we increase the temperature, we favor the decomposition, make the conversion of methane. But on the other hand, the water gas shift start working less, and we have more carbon monoxide at the end. So we need to have this trade-off here that we need to work with our colleagues that are working on the process simulation to understand what's the best point for us to work. So we start those experiments with fixed temperature about 650 degrees and a fluidization velocity of 0.03. And with steam to our ratio, I call it steam to our ratio because we are dealing with syngases. So instead of just looking at steam to carbon ratio, we look at the stoichiometric steam required, and we are applying the double. So whenever you see steam to our ratios here, you know that it's proportional to the stoichiometry. So we go to our first experiment that we run. Are you there?
3 minutes left.
Okay. Yeah. So when you go to the first experiment that we run, that was with the syngas coming from Milena and the catalytic tart tracking and the converge catalyst. Here you have the comparison of two cycles. Okay. In the first cycle that we run, we have hydrogen at the end with over 92% of purity and concentrations of methane and CO at the end lower than 3 and 2% respectively. And when we work to our fourth cycle, which is, we also observed that our sorbent start to work better after the first and the second cycle, we have conversion hydrogen of over 95% and CO and methane under 2%, which shows that the level of conversion is satisfactory to the process that we are trying to show. But we also test these with glycerol, because since the objective at the end is to produce biodiesel down the line of the project, we are trying also to recycle some of this glycerol in the SCR process. So when we run the experiments in the SCR process with glycerol, we also have high hydrogen concentration at the end and very low amounts of CO and methane. What are the next steps now? We are still finishing the process parameters to fine tune what's the best process parameters for the Converge concept, and then we move to a 500 hours campaign in a much larger facility, which we operate in continuous mode with the double bubbling free diced bed. But this work has also been done beyond the Converge. We have also tried this into a biogas value chain to test the biogas conversion, and we have very high efficiency with over 98% hydrogen at the end with biogas production, and also CO2 purity of 98%. And this is also applied for biogas with syngas. And coming to the conclusion, what are the main advantages of that over the competing technologies? That here we can combine the reforming and the water gas shift with CO2 in only 2 reactors. And this bring intensification to the process, leading for more compact system. We have less consumables because we don't need a shift catalyst for water gas shift reactors, and also no CO2 solvents in additives. We improve the heat integration because we are working with CO2 removal in high temperature. The yields of hydrogen and CO2, they are both over 95%, which can be used for chemical synthesis such as DMB and methanol. The CO2 can be used in Power-to-X application, also be sequestrated in a BECCS format. But also the hydrogen can be used as a standalone for fuel cells for electricity or as a chemical. And later but not least, this can be used for glycerol also, so some liquids. All these together, they bring advantages of this in CapEx about 20 to 30% related to the conventional technologies. I wait for your questions either here or after. Okay. Thanks so much.
Thank you, Antonio. Unfortunately, you passed your time. So there is no time for questions. If you have questions for Antonio, you can use the chat. Antonio, you can answer chat. So please, now we move to the next presentation. If you are so kind, Antonio, to switch off your micro and your camera. It will be given by Serena Poto. It's about membrane reactors for dimethyl ether production. So again, I kindly ask you to switch on your camera and your micro, Serena, and please leave some minutes for questions and don't exhaust your time. Thank you.
Hello, thank you. Hello, everybody. Can you see my screen?
Yes.
Okay, so good morning. I'm Serena from TUE, and with this presentation, I will show you our work that we carried on in the framework of CO2 fuel project regarding the CO2 direct hydrogenation to DME via membrane reactors. Nowadays, the problem of greenhouse gas emission is well known all over the world, and CO2 is the most problematic gas due to the very large amount of CO2 emitted every year from several sectors. Among the different possibilities we have to mitigate the CO2 footprint on our planet, the most promising one is the CO2 capture and reconversion into more valuable products or energy carriers. And the CO2 fuel project focuses on this topic in particular. The main target of this project is to avoid about 2.4 million tons of CO2 every year by proposing 2 different alternatives for the CO2 recycling. And our role in this project in particular is to focus on the development and upscale of DME production from CO2 in collaboration with Tecnalia. Why dimethyl ether? DME is a very interesting molecule due to the similar physical properties to the LPG, which make it a very good candidate as transportation fuel. Dimethyl ether is the product of methanol dehydration, therefore there are 2 possible routes for its production. The indirect one, which requires 2 consecutive reactors, one for the methanol synthesis and one for its dehydration, and the direct route, which combines the 2 processes in a single reactor, where usually physical mixture of the 2 catalysts is placed. The main advantage of this direct route is that it is less limited by thermodynamics, since methanol is continuously subtracted from the equilibrium due to its conversion to DME. The only drawback is that the downstream DME separation from the unconverted gas is more complex. Nowadays, however, the main source for the methanol and DME production is syngas, and the syngas production itself can produce further CO2, and also according to the composition of the syngas, the stoichiometry of the process can lead to the production of CO2 rather than to its consumption. In this project, we want to promote the direct DME synthesis from CO2, and the 3 independent reactions occurring in the process are shown here. CO2 is first hydrogenated to methanol, according to the first reaction, and then methanol will be dehydrated to DME according to the reaction 3. The reverse water gas shift is an undecided reaction that leads to the production of CO. According to the thermodynamic considerations and also considering as you can see, however, all the reaction leads to the production of water, which poses a very strong thermodynamic limitation to the process, and also water is known to deactivate the acid sites of the zeolite catalyst. So a promising solution for this process is the in situ water removal from the reaction environment that we can do by using a membrane reactor. A membrane reactor is a unit where reaction and separation occur simultaneously. And when the membrane is correctly chosen, in this case, the membrane can allow for the selective water removal from the reaction environment, shifting the equilibrium of all the reactions toward the right, overcoming then the limitations and also avoiding the catalyst deactivation. The membrane to be appropriate for this process has to fulfill some requirements. First of all, it has to show affinity to water, and also it has to be stable within the process condition and hindering gas permeation at the same time. Different types of membrane are already available on market. They also show good performance in terms of permeability and selectivity, but these membranes have several stability problems. So in this project, we would like to focus on the carbon membranes, which are known also to be stable up to their carbonization temperature, and we also have the possibility to tune their properties and make the carbon membrane to be hydrophilic. The goal of this project includes the development of carbon membranes. In particular, the membranes are developed at Tecnalia and tested at UE, and then the development of a 1D phenomenological membrane reactor model in order first to study the effect of the membrane properties on the reactor performance to set a target for the carbon membrane development, and then the optimization of the membrane reactor operating conditions by also proposing an alternative way for the heat management. And of course, the main objective of our project is to promote a valid alternative for the CO2 valorization. The carbon membranes derive from a pyrolysis of the polymeric precursor, and in this project at Tecnalia, they developed in-house polymeric phenolic resin called Novolac in acidic media. Out of this polymer, a dipping solution is then prepared. In particular, you can notice that we had 0.8% of boehmite nanoparticles in order to give extra hydrophilicity to the membrane, introducing then OH groups. The alumina support is then deep coated into this dipping solution and dried overnight under continuous rotation, and afterward the carbonization takes place, and during the carbonization step several process parameters can be regulated, such as the carbonization temperature, the inlet atmosphere, or the heating rate. The main transport mechanism for carbon membranes is the molecular sieving, and according to this mechanism, gases are separated according to their kinetic diameter. And since water is the smallest of the molecules involved in this process, it also shows the largest permeation flow. However, the higher permeation flow of water can be also attributed to the affinity of water to the surface of the carbon membranes, as you can see in the figure here on the right. So we also believe that water permeates through the membrane according to adsorption diffusion mechanism, or also capillary condensation in the smallest pores. Here we show the performance of one of the best membrane that we tested, and you can see that water has the highest permeation flow at each temperature condition. And we also tested the methanol permeation, and the membrane showed a good perm selectivity of water with respect to methanol. Now I will move on to the membrane reactor model for the CO2 hydrogenation. The fixed bed membrane reactor that we studied in this project is characterized by two coaxial tubes. The inner one is the membrane, while the outer shell is the so-called reaction zone, where the catalytic bed is placed. A mixture of CO2 and hydrogen is fed to the reaction zone, and as we said before, this mixture in contact with the catalyst will produce a large amount of water that we want to permeate through the membrane. The flux of a species across the membrane is described by the product of the permeance and the driving force, which is represented by the gradient in partial pressure. So in this study, we propose an alternative way to promote the water removal, which is the circulation of a sweep gas in the inner tube of the membrane, having the same composition of the feed, so a mixture of CO2 and hydrogen, and also with a pressure that is slightly lower than the reaction zone one. In this way, we will keep high only the driving force of water, because water, when permeating through the membrane, will be diluted into the sweep gas. Also, if the sweep gas will be circulated with a lower temperature with respect to the reaction zone, we can also promote the heat removal from the packet bed. We adopted a co-current configuration since the highest driving force for both the water and heat removal is at the entrance of the reactor, where the reactions are faster. Model equations include mass and energy balances for reaction and permeation zone, and a momentum balance, in particular the Ergun equation, to have an estimation of the pressure drops across the catalytic bed. The reactor performance are determined in terms of conversion and yield of the products, but we also adopted a correction to take into account the possibility for CO2 or products to permeate through the membrane. In particular, for CO2, we can have a loss of the reactant due to its permeation, or a reactant co-feeding due to the back permeation. An interesting variable is the water removal amount, which represents the efficiency of the water removal and separation in the membrane reactor. We first use this model under isothermal condition in order to assess the effects of the membrane properties, and then we optimize the operating condition by using the sweep gas for the heat management. In particular, we optimize the temperature to both reaction and permeation zone, the gradient in total pressure, and also the SW ratio, defined as the ratio between the sweep gas flow rate and the feed to the reaction zone 1. These two variables in particular influence directly the driving force for the permeation, and then we also optimize the composition, while we kept constant the total pressure in the reaction zone, and we optimized the temperature profile in order to have an average value of 200 degrees, since this value was determined to be the optimal one for maximizing the DME selectivity. The membrane properties were estimated in terms of permeance of all the species and perm selectivity, defined as the ratio between water permeance and the permeance of the other species. The procedure we follow is that we first optimize the water and hydrogen permeation flow under the hypothesis of ideal membrane, so that only hydrogen and water are permeating through the pores. And then we removed this hypothesis in order to estimate all the other species permeance. We also made some consideration on the transport mechanism, in particular water and methanol, which are condensable species under this condition, can permeate also according to a capillary condensation phenomenon, while the main transport mechanism of the gases is the molecular sieving. So according to this consideration, we made some hypotheses, and also one of these hypotheses include that DME is not permeating the membrane due to the very large molecular size. We kept constant during this study the operating condition. We first optimize the water permeance and its selectivity to hydrogen. And as you can see here, by increasing the water permeance, the reactor performance are improving up to an asymptotic value. So there is an optimum in the water permeance of the membrane. You can also notice that by decreasing the selectivity to hydrogen, we see an improvement in the reactor performance, and this is clearly due to the back permeation of hydrogen from the sweep gas to the reaction zone, since you see here that the hydrogen transmembrane flow is negative, but this is an undesired situation since we don't want to change the hydrogen concentration in both the reaction and permeation zone, also because the sweep gas can be recirculated back to the reactor without requiring the very large makeup of hydrogen. We made similar consideration also for the other species, and so we determined these values of the selectivity to be optimal for the reactor performance, while DME, as I told you before, is not permeating to the membrane. These properties showed a very good agreement with the already available membranes, ceramic and polymeric membranes, but these membranes have problems of stability, while not enough data are so far available for carbon membranes regarding this particular system, especially for the condensable species. Then, considering the membrane's optimal properties, we optimize the operating condition. Here I'm showing you the effect of the SW ratio and delta P on the reaction performance. You can see that CO2 conversion and DME yield increase with the SW ratio up to an asymptotic value, while the effect of delta P is not really significant. The reason why the performance are increasing with the sweep gas velocity is that water is even more diluted in the sweep gas, and so the driving force for its permeation is larger. And we can also see here that we reach a very high efficiency of the water separation in this condition. The temperature profile in the reaction zone is characterized by a peak named hotspot and a lower asymptotic value. And here we show the effect of the SW ratio and delta P on these temperature values. Of course, delta P has not an effect on the heat management. On the contrary, while increasing the sweep gas velocity, the asymptotic temperature value is decreasing. And this because by increasing the velocity, we are increasing the heat transfer coefficient. So the heat management is more efficient. The temperature profile was then optimized also by tuning the inlet temperature to reaction and permeation zone, and considering that we don't want to overcome the catalyst deactivation temperature and that the temperature has to be at least the temperature at which the catalyst is active. So here we show the operating condition which optimize the heat and water removal. Here is a resume of the optimal conditions for the membrane reactor. You can also notice that the hydrogen to CO2 ratio is slightly higher than the stoichiometric value. And this is a very good aspect of the membrane reactor because it consistently lowered the hydrogen requirements with respect to a conventional one. With these variables, we can have 36% of improvement in CO2 conversion and 43% in DME yields with respect to the thermodynamic limitation. And here we show the temperature and the water concentration profile in both the reaction and permeation zone along the reactor. And we see clearly that the highest driving force is required for both the heat and water removal at the entrance of the reactor. And that by using the sweep gas for both the heat and water removal, we have a very similar trend in the profile of these two variables. As conclusions, the alumina-supported carbon molecular sieve membrane that were synthesized at Tecnalia showed very high value of water permeance, which already matched with our requirements. There is no need to have the highest membrane performance since there is an optimum in the water permeance and also selectivity. The sweep gas, when circulating in the inner tube of the membrane with a higher flow rate to the reaction zone, can promote both the heat and water removal. The co-current configuration has several positive effects. We saw that the highest driving force is at the entrance of the reactor, and also in this configuration we avoid water back permeation. The operating conditions were optimized, and we show also that we don't need a large value of the gradient in total pressure, and this is positive for the membrane mechanical stability. And with our optimized condition, we were able to overcome the thermodynamic limitations with a 96% of efficiency of water removal. Thank you for your attention.
So thank you so much for your very interesting presentation. So congratulations for the results. So to you and also to the team working in Eindhoven, and especially the group in Tecnalia doing the membrane. So it is an excellent work and great news for, I think, our community. There are no questions in the chat. Then I will make one question and then we move into the next speaker. So why is the pressure difference not improving the flux of water? Because in principle, it is a way to improve the driving force, the same as increasing the sweep flow.
Yeah, so we saw, I can maybe go back to the slide. We saw that also the delta P is affecting the performance of the reactor, and so also the water removal positively. So we also tested a difference in total pressure of 35 bar, but since we are circulating the sweep gas, we also saw that the effect of the sweep gas is much more evident on the reactor performance.
Yeah, that was my question. Yeah, why is better? Yeah, but maybe
it's better also because it's better also because with the delta P, when increasing delta P, we are also affecting the selectivity of the reaction, because we are then also improving the CO permeation at the same time, as you see here. So CO permeation then will also enhance the reverse water gas shift, and then the CO yield is increasing. So that's the reason why we have an improvement of the performance more with the sweep gas flow rate than with the delta P.
Very interesting. Have you seen any type of decay in the catalyst, especially because it is well known that there can be a diffusion of cations into the zeolite like copper or zinc? Have you observed that, or have you planned any experiments, long-term experiments in future?
Yeah, we haven't seen this yet. So we tested some commercial catalysts, but we didn't go into detail yet. But yes, of course, it's a very interesting.
Okay.
Okay.
So thank you so much for your very nice presentation and answers. So now we move into the next presentation that will be given by Professor. I think she was there. Yeah. Okay. Good. Okay. I think she's she left the session. I think she has rejoined. Okay.
Yes, sorry. I tried to share my screen and then I lost the connection.
Yeah, don't worry. Try again. No problem.
Yes. Then I need to find here. Yes.
Yeah. Okay. Yeah.
So
Perfect.
do you see my screen now?
Yes, perfect. Everything works.
Okay. Good afternoon, everyone. I'm Unni Olsby. I'm working at the University of Oslo, and I'm the coordinator and catalyst development manager within the COSMOS project. COSMOS, as presented by Rick Hine yesterday, is aimed at thermocatalytic conversion of CO2 to propane and propene in a single reactor over a tandem catalyst. So catalyst development is the largest work package in COSMOS, and 7 of the 11 partners are involved in this development phase in a highly interactive manner. So among technologies to to convert CO2 to light olefins or propane and propene, then we see that the indirect manner via methanol and methanol to olefins gives higher selectivity to C2 to C4 olefins compared to the Fischer-Tropsch technology. This technology was developed for conversion of natural gas and coal, but can also be used for CO2. Now, the main challenge with this technology is that the steps of the process are carried out at very, very different conditions. And so temperatures and pressure, and this requires heat transfer between the various reactor steps. And this is only accessible for large plants and not suitable for smaller plants like we foresee for CO2 conversion. So what we aim to do in this project is then to take off gases from steel and refinery industry and convert them with hydrogen in a single reactor to form propane and propene. A main advantage of this process, as Rick Hein also presented yesterday, is that the Gibbs-free energy of forming the desired products, propane and propene, are much more favorable than formation of methanol in the whole temperature range. And that means that we can drive the process towards the desired products. Also, CO production is more favored than methanol production, and especially the undesired methane is favored in the whole temperature range, as we see here. A challenge of this tandem catalysis is integration of the two processes, because methanol formation is favored at low temperature, but the methanol conversion into propane and propene is favored at higher temperatures. And in particular, we know that the mechanism of reaction from methanol to hydrocarbons in zeolite type catalyst is based on alkene methylation cracking, methylbenzene formation and dealkylation. But this dealkylation step, it is only favored at temperatures about 300 degrees and more favorable about 350 degrees. And that means that if we operate at low temperature, then these methylbenzenes will instead be converted to coke. And this is observed from this study here from Professor Schulz, where you see an exponential increase in catalyst lifetime when you go from 250 up to 400 degrees Celsius of operating temperature. So what we need to do for the zeolite component of the tandem catalyst is either to favor only this alkene cycle, which means we need to use zeolites with very narrow pores, and those are not very active. So, and the other thing we could choose was then to use conventional MTO catalysts and operate at higher temperature. So our starting point here was using two commercial zeolites, so the Cabasite SAPO34 and MFI ZSM5, that have both been shown to yield high yields of propylene under different conditions. For the CO2 hydrogenation candidates, we were looking for a candidate that could operate at higher than 300 degrees C and at moderate pressures. And we gathered all the literature that was available when we started the project, and we see this is in black 350 degrees. Only a few of these catalysts have been tested under such high temperature. And we also see that increasing the temperature gives lower selectivity to methanol, typically for all of them. And also, if we look at the pressure instead, we see that they are typically tested at high pressure. Now, among the catalysts, we saw that there were a few that gave high selectivity to methanol. And among them, we selected two, palladium zinc oxide and zinc zirconia as starting point. And going first to this palladium zinc on zinc oxide, we prepared it in two different ways, either to impregnate palladium salt onto zinc oxide and then physically mix with ZSM5, or we impregnated or we grafted a palladium complex directly onto mesoporous ZSM5. And in each time we reduced the catalyst in hydrogen flow. And what we could see from TEM images, as we see here, but also from X-ray diffraction, we see that upon pre-treatment in hydrogen, we see that we form the mixed palladium zinc alloy. And we also see that when testing the catalyst, we see that with time on stream, we see an increase in the methanol selectivity, which is typical for which is coming with the palladium zinc alloy formation, as also known from literature. However, when we mix this ZSM5, the palladium zinc catalyst with ZSM5, we did not observe hydrocarbon formation as we were expecting. And what we could see was that instead we formed still methanol and we formed some dimethyl ether. And this means that something has happened to the Brønsted acid sites that would normally form hydrocarbons under these conditions. And indeed, when checking the amount of Brønsted and Lewis acid sites using pyridine as probe molecule and IR spectroscopy, we see that the Brønsted acid site concentration, when we grafted palladium and zinc onto the ZSM5, the Brønsted acid site disappeared immediately, and there were Lewis site formation instead. Whereas the palladium zinc on zinc oxide that was physically mixed with ZSM5, we see that it is only upon activation that we see that the Brønsted acid sites disappear and that we see formation of Lewis sites instead. So XOS experiments on the same catalyst showed that what happens here is that zinc is volatilized and it is ion exchanged onto the Brønsted acid sites of the zeolite, and this shows an additional challenge with these tandem catalysts that they may poison each other. So more detail about this study can be found in this paper that was published last year. And then if we go to case 2, we we prepared zinc zirconia catalysts by co-precipitation and with different zinc contents. And what we could see here was that there was formation of this this zinc zirconia mixed oxide phase. And we could also see that upon pre-treatment in hydrogen, we would form more of the low coordinating the zirconium sites, and those are the active sites for the methanol formation. When we tested the catalyst and with different contact times, increasing contact times, we see that we have an increasing CO2 conversion, we have decreasing methanol selectivity and increasing CO selectivity, suggesting that methanol is a primary product of reaction. However, when we look at the yield of methanol, we see that it increases and then decreases, and this is not typical for a primary secondary reaction sequence. But what we found in agreement with what other presenters have said is that this is really related to the formation of water, which is not only formed with methanol formation, but also with CO formation. So if we plot now the equilibrium quantity of methanol together with the experimental points, we see that equilibrium is obtained at quite short contact times. Mixing this catalyst with 2 different ZSM5 samples, we see in each case that we have the same effect here, increase in conversion with increasing contact time, decrease in oxygenate and hydrocarbon formation with increasing contact time, and increase in the CO selectivity. But then again, we wanted to know whether methanol content was still at equilibrium, and we see that this is certainly not the case. Methanol is at a much lower level than what you would expect from equilibrium. So this means that the methanol to olefins catalyst is very active. And both this and also the fact that the CO2 conversion level was not affected by mixing with ZSM5 is a strong indicator that it is really the methanol formation which is the rate limiting step of this tandem reaction. Another interesting feature is that the CO selectivity decreased with an increase in the Brønsted acid site concentration in ZSM5, and this indicates that what happens here is that CO is mainly a secondary product formed via methanol, and then when you mix with the zeolite, then you have competition for a conversion of methanol either on the Brønsted acid sites to form hydrocarbons or on the zinc zirconia catalyst to form CO. Yes, computational studies show that it is the hydride transfer and to form formate or also to hydrogenate the formate species that seem to be the rate limiting step of methanol formation. And this study is also published. Well, it's available online this year, so you can go to that paper to know more. And then my third and last case is on a system where we used both zinc zirconia catalyst that was not known from literature before, and also mixed it with the RUB13 catalyst. And this RUB13 is quite similar to the SAPO34. It has a cavity window structure, but the window is a little bit larger than what we see in SAPO34. And what we observe when we compare the various catalysts here, we see again, as expected, that the zeolite has no influence on CO2 conversion, but it does influence the selectivity to CO. And also, of course, the distribution of hydrocarbons. Furthermore, what we see here is that the RUB13 catalyst, as I said, it has slightly bigger windows than SAPO34. And we see that while SAPO34 favors ethene and propene formation, and then butene as the third largest product, we see that this distribution is shifted here. So we have mainly propene again, and then butene with ethene on third place. So we see that the C3 and C4 selectivity was up to 70% over the RUB13 catalyst. When we go to the test conditions, we see that with an increase in hydrogen to CO2 ratio, we see that we increase the CO2 conversion, presumably due to higher selectivity to methanol in the first step, and at the same time decrease the selectivity to CO. But then the distribution among the hydrocarbon products was unaltered in this range of hydrogen to CO2 ratio. Again, we saw that it is hydrogen transfer reactions that seem to be rate limiting for the methanol formation. And we see that we could have up to 90% of C3 and C4 olefins in the light olefins fraction due to this promotion of alkene-based cycle that was shown in this case. And also this work has been published. So that was the advantage of spending much time at home, that we could spend more time thinking and writing. I will not use more time on this, but only say that through these 3 case studies we see some important features of the tandem system. One is the possibility of poisoning from one component to the other. Another important feature is that we see that testing, I have not shown that here so much, but the combination of the methanol formation and the methanol conversion catalyst seems to be very very important, and this is something that we are currently working to explore in more detail. So finally, I just want to thank all my Cosmos VP1 partners for their contributions, and finally, thank you for your attention.
Thank you so much for your very interesting presentation with a lot of results and very nice science behind. So we have one question in the chat that is from Fernanda Neira Angelo. So have you compared with two-step processes, and can you comment on the stability of this catalyst?
On the, sorry, on the...
It's on the chat if you want. Have you compared with two-step processes? I mean, one after the other, two reactors, I imagine. And can you comment on the stability of this catalyst tested separately, I guess? That is the question.
Yes. First of all, we have tested the catalyst separately and in tandem, and what you see is that the conversion to the products is much higher when you test in tandem, because you are driving the equilibrium of the reaction towards the hydrocarbons, and not it is no longer so dependent on the methanol formation equilibrium. And when it comes to the stability, what we observe is that the stability of these cavity window structure type zeolites and zeotypes is much higher in the tandem reaction than when they are tested separately. And this is true both if you test the catalyst as a dual bed catalyst and when you physically mix them. And studies in literature show that adding hydrogen is important for the stability of the catalyst, and the same with water. So it is probably an effect of the co-feeding of the methanol with these other components that improve the stability of the system.
Okay, thank you. I don't think there are more questions in the chat. Maybe I can make a last question. Maybe I don't know if you can share your ideas about how to prevent the diffusion of cations into the zeolite, which strategies about the structuring of the catalyst, how you will combine the two phases in separate granulates or core shell or other approaches that you think it will be interesting for this, especially when you have a lot of water in your reactor?
Yes, I mean that's a very good and quite complex question, of course. The one thing that we need at least to consider is to avoid having, like in this case, having a surplus of the volatile zinc phase.
Mm-hmm.
Yeah, we are looking into the stability of mixed oxides with zincs right now, and I don't have the answer yet, so I don't know but it is maybe having a sort of a diffusion shield between the two phases would be a solution, as you say, for shell, for instance. Yes, clearly.
Okay, very good. So thank you so much for your very nice presentation and answers.
Thank you.
Now we move into the next presenter, that is Dr. Krishnamurthy, that is about CO2 capture using 3D printed PEI absorbents supported by carbon nanotubes. So please.
Can you hear me?
Yes, we can hear you. It will be great if you can switch on your camera.
Of course.
If you are visible.
Yes. Do you see my slides now?
Not yet.
I'm sorry, let me try to share my screen again. Is it loading? At least
we can see a black background, but not your screen.
Okay. I'm sorry, I'm trying to, because there are too many. Yes, now I see it. Now I guess you should be able to see it now.
Not yet. No.
Let me try again.
Try again. If not, maybe you can send the presentation to the organizer, to Alexandro, and he can share.
Yes.
I think we cannot see you.
I think it's better I send the presentation. So,
Alessandro, are you there? Yes. So maybe you can send to Alexander by a private chat.
Yes.
Okay.
Yeah.
So if you do that, we wait for you. If not, we move into the next presentation.
Yes, I can do that. Yes. I'm really sorry for this.
Alessandro is there.
Can I have your, if it's possible, like an email address that I can send it?
Okay, Alexandro, or you can send to Fernanda or Alexandro. Maybe if you look at the chat, they will write the email. Okay, I think maybe you can chat separately. Alexandro, can you help us with that, or Fernando, while we move into the next presentation? I hope Susana Perez is prepared for that. Sorry for this.
Yes, I am here.
So we take you now, if you agree, and at the end of the session, we'll move to the presentation of the other project. Okay, so if you can share your camera and your presentation, would be great.
Well, but I think that I sense the same problem. I can see I can share my presentation. Wait a moment.
Sorry, I meant Jose has organizer, but if you want, I can share my screen for you. I can share my presentation.
Okay. I don't see my. Well, okay.
Yeah, in principle, you have the rights to present.
Yes, I have here. Could you see my screen?
No.
No.
Just wait. Maybe it gets some time to load.
Well, I'm sorry.
Okay, we cannot see it.
No.
Try again.
Okay. Now?
No.
But I'm sorry.
I will try to share.
Yes, I'm shared my.
That happens sometimes. Alessandro, any suggestion?
Yeah, I will share my screen in a minute. I'm downloading presentation.
Okay.
Okay, you are downloading the presentation, not from Krishnamurthy, or?
Yeah, he sent sent via chat.
Yes, I have it as well. If you want, I can try to share. Let me see if that works or not. Can you see my screen?
Oh, yes.
Oh.
Not more.
Oh, I don't know what happened. It is something with the Teams. I think in this case we are guilty. We are not guilty.
Okay, now we see.
Yeah. Okay. Then we go through this one if you agree. Sorry, Susana. And then if you can post your presentation in the chat, we'll do in the same way. Okay.
Okay.
Okay. So.
Yes.
You don't need my help.
That was already fine. Thank you.
Okay.
Okay, yeah, thank you so much. And my apologies for not able to share the presentation before. So this work is a part of the Karmov project that Adolfo had presented yesterday about, and there is also a parallel session which just happened a while ago with Dr. Kamerlopoulos presenting some work on the hybrid membrane vacuum spring adsorption system. So this presentation is mostly on post-combustion carbon capture. That is to study 3D printed sorbents for that contain polyethylene imine and carbon nanotubes. If you can go to the next slide, please. Yes, thank you. So when you talk about post-combustion carbon capture, the main challenge is the size of the capture unit. And if you consider a packed bed system, if you want to bring down the size, you want to have fast cycles and operate the cycles at very high flow rates. But the main challenge, as I said, with the packed bed system is that you have a high pressure drop, and to overcome this pressure drop, you have to do more work. Instead, you can switch to structured sorbents like laminates or monoliths. And one technique that is gaining very popularity over the last few years is 3D printing. And the advantage of 3D printing is that you can have good control over the shape of the structured sorbent as well as the channel dimensions. So this work is a multi-scale study on evaluating one such 3D printed sorbent. And in this work, the 3D printing is done by a technique called robocasting, which is computer-controlled extrusion of a pi carbon nanotube paste that is based in water. And the structure is then done dried for post-treatment so as to do the testing of the structure. The next slide, please. Sorry, yeah, thank you. So here, like any classic adsorption process, you want to obtain the adsorption equilibrium first, and that is done by two methods here. One is volumetric system, which is a static system, and the other one is a breakthrough system, which is a flow system. So in the breakthrough system, you basically introduce a step change in concentration, a feed containing a known amount of CO2. That is for the adsorption step. And to do the desorption, to take out the CO2 from the solid, you simply purge with the inert carrier that you had used in the adsorption step. And in this case, it is nitrogen. For the breakthrough system, we used about two structures, which are total 4 centimeters in height. And for the volumetric system, we had to crush one of the structures because the volumetric cell was not big enough for the structures. And if you see the graph on the left, which is the adsorption isotherms, as expected for an amine containing adsorbent, the nitrogen sorption is more or less negligible, whereas CO2 adsorption is far more higher than that of nitrogen. And we also, when we did the volumetric testing, we also took samples from two different parts of a single structure. One is actually a part of the structure that constitutes the channel walls. The other one is the external part of the structure, and we can see some minor variations between the CO2 adsorption capacities between two parts of the structures. Next slide, please. Then we used the help of modeling to extract the information on adsorption kinetics for CO2 adsorption in this adsorbent. The way we did was we modeled the adsorption step using a standard adsorption process model by fitting three parameters. The isotherm parameters were fixed, but we fitted three parameters, which is the linear driving force coefficient, or the rate constant for the adsorption rate from the gas phase to the solid phase, and the internal and the external heat transfer coefficient values. And as you can see here, you get a good match. But what do you observe in the breakthrough is that you have a small kink. I'm not sure if that is very visible here, but it's a very minor kink. And that we suspect is because of the fact, two things. One, we observe cracks in the structures post drying. So some of the channels, you can see some small gaps. You don't have the channel walls. The other one, if you can look at the picture of the monolith here, you have non-uniformity in the channel sizes, which is basically on the edge of the channel. So these two things can cause such kinks, but nevertheless, this is not going to impact in have a great impact in terms of your estimation of the kinetic constants. Next step, please. Next slide, please. Then we, the next slide, the previous one, sorry. Sorry, you have to go to, I think, slide. Yeah, this is the one. Thank you. So then we move on to a process-based study. So for this work, we have taken a representative coal-fired power plant to start with. This feed contains 15% CO2, 85% nitrogen, and that is at 90 degrees Celsius. We have chosen a 6-step vacuum swing adsorption cycle. So these are the 6 steps that a single column undergoes. I'll briefly explain these 6 steps. The first step is the adsorption step, where you introduce a feed and you collect nitrogen at the product end. The second step is called a rinse step. Basically, you are enhancing the concentration of CO2 inside the column by introducing a stream that contains more CO2 than the feed. The third step is called co-current evacuation, where you evacuate the column from the top because you want to remove the nitrogen so as to enhance the purity of the CO2 when you do an evacuation in the counter-current step. That is the fourth step. You do a counter-current evacuation because CO2 is strongly adsorbed and it is usually located close to the inlet. So you want to do a counter-current evacuation. Finally, you do the fifth step is a purge or a light reflex step. The purpose of this step is actually to remove the CO2 that is still remaining in the column. You're not actually using this for the product because it is a low purity CO2 stream, but it contains enough CO2 that is higher than that of the feed. So you recycle back entirely to do the rinse step. And finally, you want to prepare the column for the adsorption step. So you repressurize it with the remaining nitrogen product from the adsorption step. The performance of the process is described by 4 performance indicators, namely CO2 purity, recovery, productivity, and the specific energy consumption. And ideally, you want to have a process that contains 95% purity, that can give CO2 at 95% purity and capture 90% of the CO2. The model equations, we simulated this process in MATLAB. The model equations are exactly same as that of the packed bed, except for 2 different correlations. One is the correlation for the pressure drop, and the previous speaker had spoken about Earthen equation, which is commonly used for packed beds, but here we have a correlation for a monolith, and then the axial dispersion equation is different from that of a packed bed. So these are the 2 differences. Next step, please. Next slide, please. In case of an adsorption process, you have multiple steps, multiple pressures that can affect the performance of the process. So if you want to get to know the true minimum of a process, then a simple parametric study may not help. So for this, you need to have an optimization routine that can do hundreds of thousands of simulations, or at least thousands of simulations, that can give you the true minimum of a given cycle configuration and an adsorbent. And these mechanisms, these algorithms are called nature-inspired algorithms. And I say the word nature-inspired because I have a picture down which more or less mimics the reproduction of a cell. And these algorithms have exactly the same function. It's just that a computer does this job for you. And I have included a picture of a Rubik's Cube because to explain the process. So if you consider a Rubik's Cube, you want to have the objective or the constraint here is to have a unique color in every face. I'm sorry. Unique color in every face. So you move this, you play with the Rubik's Cube with rotational motions. So this is the principle for a genetic algorithm based optimization that we are using. So we start with some initial set of parameters, and then the parameters are played with by variables such as mutations, crossovers, which are more or less similar to that of a cell reproducing. And then you arrive at the final conditions. So here we have done 4,200 simulations, and the results of after 4,200 simulations are shown in this corresponding slide. We plot as a trade-off plot between specific energy and productivity, and the minimum specific energy is about 0.7 megajoules per kilogram of CO2 captured, and this is on an electric basis. And all these points that are shown in the graph here, they are basically having cycle times of 2.5 to 3 minutes, and the absorption step duration is about 40 to 60 seconds. So to conclude, if I can go to the next slide, please. So to conclude, we were able to achieve 95% purity and 90% recovery targets. The minimum specific energy is about 0.72 megajoules, but if you convert this to a thermal basis to compare with amines, this is more close to monoethanol amines than the new amines like Selexol or CSER process. Therefore, we need to do alternate cycle configurations that can improve the performance of the process. And the second thing here, we have not considered the presence of water, or we have not considered the presence of oxygen. The presence of oxygen in a flue gas can actually affect the performance of these adsorbents. So you cannot operate it beyond a certain temperature above 110 or 120 degrees Celsius. So that is something that we need to take into consideration when we design a cyclic adsorption process with respect to these adsorbents. Next slide, please. We also had some challenges with respect to 3D printing. One was that we had a lot of water in the paste, and that means that we had two-phase or phase separation while printing. And to overcome this, we had to make use of binders. And that means we reduced the capacity of the printed structure. And we also observed high shrinkage. This may not be a challenge in large scale systems, but when we are going for large demonstrations, then we will have problems in choosing the right dimensions for the demonstration. And finally, we also had some pressure drop issues. The predicted pressure drop was always less than that of the measured pressure drop, and that was because of the fact that we had cracks in the structure. So these are the things that we need to overcome if we want to have a successful 3D printed structure for large-scale demonstrations. So with this, I would like to conclude. Thank you very much for giving me this opportunity, and I'll be happy to take in some questions.
Thank you so much for your presentation, and especially in these conditions that virtual meetings are sometimes crazy. So I don't know if there are any questions in the audience. They are not in the chat. If not, because we are already behind our schedule, I would suggest to move to the next one. But before, I want to thank you again for this very focused presentation. So now we move into the presentation of Susana Perez. Let me try to share the screen. 1 second. Hopefully that will work.
Yes, thank you very much. Yes.
Okay, you can start.
Thank you very much. Well, good afternoon. My name is Susana Perez. I belong to the energy area of Tecnalia. My work is related with the chemical synthesis from CO2 to obtain different products, and also with the development of a multi-structure reactor based on process intensification. Next slide, please. So today I'm going to speak about what is process intensification and microreactors applied in chemical synthesis, the Tecnalia milli-reactor, and the results obtained with this milli-reactor in Sabatier process. Next, please. Well, as you know, CO2 emissions must be reduced if we want to avoid the global warming of the planet. For this, CO2 must be captured and used. Among its application in chemical synthesis are the production of urea, methanol, organic carbonates, methane, or formic acid. But with the current thermocatalytic reactors, the yield and efficiency of the process are low due to the poor mass and energy transfer. A way to improve the mass and energy transfer is by intensifying the process through the use of microstructure reactors. Next, please. Sorry, next slide. Thank you. But what is a microreactor? Well, to define a micro and milli reactor, we can focus on the denomination given in literature. According to this, the dimension of the internal diameter of each channel of the reactor defines its name. So between 10 to 1,000 microns is called a microchannel reactor, and between 1 and 10 millimeters is called a millireactor. So a microstructure reactor is a system that seeks to develop processes more efficient with lower operating costs that generate the least possible amount of waste, safer, smaller, and that obtain the greatest quantity of product with the least consumption of raw materials compared with the conventional reactors. In chemical synthesis, the use of microreactors improves the transfer mass and energy between the three phases involved in the reaction: gas, liquid, and/or solid. Next slide, please. Yes, okay, thank you. In literature, the method for manufacturing this reactor is microstructuration by assembling individual metal plates with various phases. The reaction channels are made on these plates by micromachining techniques, and the catalyst is fixed in these channels. The plates are superposed and joined together by welding to form a battery suitable for the selected flow rate. Finally, a certain force is applied to the reactor at high temperature under vacuum. However, this processing technique can generate deformation in the material used. On the other hand, another problem of this configuration is the catalyst replacement, because if the catalyst is deactivated during the reaction, all the reactor must be replaced. The next slide, please. Following, we can see some different kinds of microstructure reactors appears in literature, applied to chemical synthesis like methanation of CO2, selective oxidation of CO, methanol reforming, or Fischer-Tropsch synthesis. In all these reactors, the catalyst is deposited in the plates that set up the reactor. What is a problem if the activation of the catalyst occurs? Next slide, please. To solve the problems that detected in the microstructure reactors, Tecnalia has developed a milli-reactor consisting in several tubes with internal diameter from 1 to 4 millimeters. This design improves the mass and energy transfer in the process. In this slide, you can see the reactors already manufactured, that is from 16 to 97 channels in reactor. In all this reactor, the catalyst is filling each channel of the reactor. Next slide, please. Okay, thank you. This design allows obtain a high area per volume rate in the reactor, which increases the mass and energy transfer in the reaction. Also, the design carried out allows to obtain an uniformity in the tubes. This avoids the formation of preferential paths of reactants. In addition, the reactor has good thermal and mechanical stability to support the condition of the reaction. Also, in this reactor, the catalyst is filling the tubes, so it is easy to handle it, allowing its replacement after its deactivation. Obliged to obtain all these features in the reactor, we have selected the selective laser melting as manufacturing method. This is by 3D printing. This method allows us to manufacture the reactor faster in a single piece with low cost and with a flexible design. The construction material in all the reactor is stainless steel. Next slide, please. So the features and advantage of the design of the following are the following. There is an intimate contact between gases and catalyst, so a high mass transfer is obtained with increase the performance of the reaction. The reactor has low volume, which reduces the pressure drop and saves production materials. The scale-up of the reactor is done by replication of the single unit, so it's very easy. To remove the heat during an exothermic reaction, the reactor is submerged in a thermal fluid, which favors the heat transfer. Next slide, please. So this reactor is appropriate to carry out exothermic reaction that need a good mass or energy transfer in the process. We already have tested this reactor in hydrogenation reaction, in the production of acetone from butanediol, and in the CO2 transformation to methane, methanol, or dimethyl that is being carried out in the CO2 Focus project. Next slide, please. To demonstrate how the developed milli-channel reactor offers better performance than a conventional fixed bed, I present the result obtained in the Sabatier reaction. The Sabatier reaction is the hydrogenation of CO2 to obtain methane and water. This exothermic reaction is carried out at low temperature and with high pressure with a nickel or ruthenium catalyst. The reactors normally used in this reaction are 2 or 3 fixed bed reactors in series, with heat exchangers between them to maintain the temperature of the process. So the milli-channel reactor tested has 16 channels with an internal diameter of each channel of 1.75 millimeters. The other reactor has an internal diameter of 9 millimeters. The catalyst used was a conventional nickel alumina catalyst with a particle size minor of 220 microns. All the stress conditions, space velocity, catalyst mass, and molar relation between hydrogen and CO2 were fixed the same for both reactors, and the gases obtained were characterized continuously by gas chromatography. We have carried out several tests to see the effect of temperature and pressure in both reactors. If the result obtained of CO2 conversion in both reactors at different temperature and pressures are represented, it can be observed that in all the conditions tested, the millichanel reactor offers better CO2 conversions. In fact, at 10 bar and 300 degrees, the millichanel reactor offers a 27% higher yield than the fixed bed one. This may be due to the fact that the mass transfer of the process has been improved due to the design of the millichanel reactor. It should also be noted that the selectivity of methane in all the tests carried out has been total. Thank you. When the multi-channel reactor has verified that offers better results than the fixed one, in Renovagas project, its scaling up was carried out. So in this project, a 15 kilobytes pilot plant was developed to obtain a synthetic natural gas from cleaned biogas. The objective was to obtain a synthetic natural gas with enough quality to be directly injected in the natural gas network. For this, a catalyst developed by ICP based on ruthenium and a 388 channel reactor with dimension of each channel of 2.2 millimeters were used. This reactor was tested continuously, and the gas obtained had the enough quality to be injected directly in the natural gas network. So this reactor in the project was integrated into a pilot plant for the production of synthetic natural gas from biogas, using an alkaline electrolyzer for the production of hydrogen. In the figure, it can see that the dimension of its equipment of the plant, being the millichanel reactor very small compared with the electrolyzer. This plant operates continuously during 300 hours with real cleaned biogas from a wastewater treatment plant. The last slide, please. So the main conclusion of the work are that technology has developed a millichanel reactor for exothermic reactions, and the reactor allows a good mass and energy transfer, is very easy to scale up by adding different channels, has a flexible design thanks to the ISLM technique to manufacture the reactor, has a huge number of potential applications, and has validated for Sabatier reaction that obtain better result than fixed bed one. Yeah. So thank you for you all.
Thank you so much, Susana. So very interesting work. So I like it very much. There are questions for Susana regarding her work on the team.
Okay.
No, I think
I am reading. It's a question from the pressure in our millichanel reactor. We have tested the reactor between 15 and 30 bar of pressure.
Very good.
Catalyst stability in the mentioned test. But catalyst stability was very nice. In this 300 hour was very nice, but the main problem was the content of the sulfur in the biogas.
Mm-hmm.
Yes.
Very good. Very interesting. Yeah. And have you observed any kind of diffusion or interaction between the material of the reactor printed and the catalyst? This is more long term, but
no, we don't. We don't see this. I'm sorry.
Yeah, because well, the printed materials are slightly different to normal piping, and it may happen. But yeah, especially.
Well, we are surprised with these printed reactors because we think that maybe they don't maintain the better conditions for high pressures, but they do. Was very nice, and the material is now suffer with hydrogen content.
Okay. Well, I said very interesting results, so congratulations. So then we can move to the next presentation. That next speaker is Dr. Francisco de Sales Vidal Vasquez. I don't know if you can share your screen.
Yes, I can. Wait a minute.
And switch on your camera.
Yes, I have. Can you see me now?
Yes, we can see you.
Okay. And now, oops.
Yes, we can see your desktop.
Yeah, sorry. I wanted to share my screen.
This is safer, so we know what you're doing.
Yeah, exactly. Yeah, I didn't want. Wait a minute. Now. I don't know why it's not sharing.
Yeah. Okay. If you make.
Oh,
yeah.
okay.
Can start. Perfect.
Yeah, I don't know why. Okay.
Thank you.
Thank you for the introduction. Well, I would like to proceed now with my presentation entitled The Kero Green Syngas Route to Alternative Fuels and Chemicals. I am Francisco Vidal Vázquez from the Institute of Microprocess Engineering at Karlsruhe Institute of Technology. So, wait. Okay. As other colleagues of the Kero Green project already presented, you can see here the Kero Green process concept, where carbon monoxide is used as an energy carrier. My presentation will focus on the carbon monoxide route to kerosene as a main process product. So I will focus on this process chain, let's say, and I will walk you through the different steps of the process, pointing out the main technical consideration of each of these steps. So first, I will talk about the water gas sieve reaction, then the Fischer-Tropsch synthesis, followed by the hydrocracking, and finally about product separation. I will also discuss shortly about off-gas recirculation. As the first step, the exothermic water gas sieve reaction is used for generating hydrogen from carbon monoxide and water, obtaining CO2 as a side product. Pressure doesn't affect the chemical equilibrium, but low temperature is required in order to achieve high conversions. For this reaction, two types of catalysts can be used: iron chromium based catalyst for high temperature and copper zinc based catalyst for low temperature. Having carbon dioxide as a side product is actually detrimental for the Fischer-Tropsch synthesis because it reduces the partial pressure of the reactants, which are hydrogen and carbon monoxide. Because of that reason, it would be actually beneficial to remove it. So here is where the so-called sorption enhanced water gas sieve becomes a suitable solution. The idea is to mix water gas sieve catalyst with solid sorbent for in situ CO2 removal. However, because of this, the reactor should be operated dynamically with two main operations that you can see actually here in the right side of the slide. So the first operation would be the sorption enhanced reaction, where we are feeding the carbon monoxide and water to the bed, and then it's the water gas sieve reaction is taking place, and simultaneously the CO2 is removed. The second is the sorbent regeneration, where CO2 is released by pressure swing assumption using steam and optionally also nitrogen as a sweep gas. This combined process has also other advantages, the particularly interesting advantage is to separate the CO2, which can be then recycled to the upstream part of the process. Well, in the actual KeroGreen concept, this is a very attractive option. For the KeroGreen project, we have developed a compact sorption enhanced water gas shift reactor. This reactor has 6 beds, which are operated dynamically in order to keep a constant outflow of syngas. Each of the bed follows a cycle which can be simplified to reaction, depressurization, regeneration, and pressurization. On the right side of here of the slide, you can see a 3D drawing of the actual reactor, where the steam nitrogen mixture for the regeneration is flow through the outer cell of the outer part of the beds in order to keep the reactor close to isothermal. The next step in the process is the Fischer-Tropsch synthesis, where linear hydrocarbons of different chain lengths are produced from syngas by a highly exothermic reaction. Here, high pressure and low temperature favor the formation of the products. Here also 2 types of catalysts can be used for reaction. Iron-based catalyst would be used for high temperature operation, and it produces shorter chain hydrocarbons, which are mainly olefins. And then cobalt-based catalysts, which are used for low temperature operation and production of longer chain hydrocarbons, which are mainly paraffins. This is the preferred option for producing liquid fuels such as kerosene. The Fischer-Tropsch product distribution can be well represented by the Anderson-Schulz-Flory model, so-called, which is based on chain growth probability, here so-called alpha. As alpha increases, the average product chain length increases. Here you can see a graphic that depicts that behavior. So what this basically means that only 2 products can be obtained with 100% selectivity, which is either methane or heavy waxes. So if you want to obtain some of the product in between, you always will have partial selectivity towards that product. On the right side of the screen, you can actually see a real Fischer-Tropsch composition using cobalt-based catalyst and how it looks like. So there is 2 main differences, which is related to the higher selectivity of methane, and then also the lower selectivity towards C2. In this product, you can see also that there is still a fraction of olefin forming, and also you cannot see here in this chart, but there is also alcohols forming, which will be capturing the aqueous phase of the product. For the KeroGreen project, we use microstructure reactor cooled by evaporating water. Due to its microstructure, the control of the reaction temperature is excellent. It has also a good performance at a wide range of operating conditions and under dynamic operation, which is these characteristics actually what separates it from conventional technology for Fischer-Tropsch synthesis reactors. This technology was developed at our institute and then commercialized and upscaled by the spin-off company Ineratec. The next step of the process is the hydrocracking. Here you can see an example for hydrocracking reaction. So just to show a simple example where a long chain hydrocarbon is cracked in the presence of hydrogen into 2 shortened chains. Where the molecule is actually cracked is also a matter of probability. On the right side of the slide, you can also see an example of what happens when you feed the full product of Fischer-Tropsch through a hydrocracking reactor. So here you can see the Fischer-Tropsch product before the hydrocracking and this after. And this also highlights the main purposes of hydrocracking, which is increase the liquid fuel fraction and consequently also remove waxes, then decrease the olefin content and increase the isomer content, which is necessary to bring the product to closer to the fuel grade. Some general considerations about hydrocracking. One important one is the that partial conversion of waxes per reactor pass is necessary in order to avoid overcracking of the product. Regarding the process design, you can consider two main configurations. One, here depicted on the right side, where you pass the full Fischer-Tropsch product through the hydrocracking, which is a simpler process configuration, but could lead to overcracking due to the presence of carbon monoxide in the gas phase. Other option is hydrocracking of only the wax phase of the Fischer-Tropsch, which is a more complex process configuration where you use pure hydrogen for the reaction, but you generally obtain a better product distribution. Regarding the last step of the process, the product separation, an easy way of separating the solid product and liquid products at ambient temperature is to simply condense the Fischer-Tropsch product at different temperature. However, as you can see here in this graphic, it's a very non-optimal separation where part of the liquid product will end up in the waxes and vice versa. For this reason, distillation is required for a sharp separation of the product and thus achieving kerosene-grade fuel. Finally, I would like to present shortly two methods of off-gas recirculation. In order to recirculate the off-gas, we need to convert it again to syngas, because that's the actual feed that you need for the Fischer-Tropsch. So the first option for doing this would be the steam reforming of the off-gas by addition of steam and heat. Another option would be catalytic partial oxidation of the off-gas by addition of oxygen to the off-gas. Each of these methods has its advantages and disadvantages, but I won't go into detail regarding this in this presentation. So coming now to the end of my presentation, I would like to mention some important points. Well, it's important to mention that in this process, we cannot reach full selectivity toward kerosene, but we can obtain other valuable products as well together with this kerosene, such as gasoline, diesel, and waxes. It is important to mention too that there is other consideration to be made, such as the heat and material integration of the different components of such a plant, where maximizing the energy and carbon efficiency is the key for a successful process concept. This is mainly due that now we are dealing with high costs for the raw materials, which are the captured CO2 and renewable electricity. Thank you for your attention. You can find, oh, sorry, why this happened? Oh, yeah. You can find more details regarding our work on sorption enhanced water gas shift and carbon dioxide-based Fischer-Tropsch fuels in these two publications. I will be glad to answer your questions. Thank you.
No, thank you so much for this interesting and nicely structured and focused presentation. Are there any questions in the audience? I don't think so. I think people is very hungry, especially yes. in
This is the last presentation.
So let me make a question. So when it is very nice that how you have explained all the sequential processes, and when you try to intensify some of them, like with the Sorption Enhanced. For example, for the case of Fischer-Tropsch on hydrocracking, this is very normal to at least in the lab to try to combine both reactions so that you have a hybrid of the Fischer-Tropsch cobalt or iron. I don't know which one you are using now, and the zeolite. Have you considered that, or you just leave out because of other reasons?
We in our institute we have been always consider these two processes separately. So subsequently, first Fischer-Tropsch and hydrocracking. There was also some experiments on mixed bed. So with actually a PhD regarding the mixing Fischer-Tropsch and hydrocracking catalyst in the same, but combining, let's say, in the same catalyst both features, not so far. I have seen some research, some publications regarding that, but we didn't focus on that.
Mm-hmm. Very good. So in another project, we are having this kind of or problems or challenges related to the separation, and then finally ending with distillation. And this is very energy intensive.
Mm-hmm.
And we are exploring. This is an old topic, or organic membranes for having like a cutoff of
Mm-hmm.
on molecular weight. Have you explored, at least on from a theoretical or modeling point of view, that?
No, actually not. And so far that I know, I think also in our institute there haven't been research on membranes. We have been working now lately in the distillation and trying to improve that through better structure packings,
Mm-hmm.
which could be 3D printed actually.
Yeah, sure. Very good. So I think that was a very, very insightful presentation. So thank you so much to you, and also
Thank you very much.
Opportunity to thank all the speakers of the session, and you for attending the session. So thank you so much, and now it's time for lunch.
Thank
Bye-bye.
you. Bye.